source and switch it to one of the other.
Right. So on my glasses, they're in my bag. I got to Walmart to buy glasses. I just found them by mistake today. It's getting cold. It's September. Here. Okay, what happened to the tokens? They're supposed to. No, these are. There's nobody here. Morning, everybody. How many people on Zoom? 71. And we have like 30 people here. Not 30, 20. All right. So this is getting uncomfortably. We're going to continue our series of lectures on training neural networks. Get your name pads out. Shut your laptops.
I'm just downloading the slide.
Sure.
Just 1 minute.
Let me begin anyway. Get your name tags out, guys. I haven't memorized your names. I know Quentin and Joshua, but that's because they're always here. Yeah, you're cool. So we're going to continue our series of lectures on training neural networks. For a quick recap, we know that neural networks are universal approximators. We train them to approximate any function. They are trained to minimize the total error on a training set, and we do so through empirical risk minimization. We use gradient descent or variance of gradient descent to do so. Gradients are computed through back propagation. So we also found that vanilla gradient descent may be too slow or unstable. So if you've gone through the slides, which you must, one can use second order methods that normalize variation across dimensions through the inverse of the Hessian, but they cannot be computed for large functions due to too many parameters. So we don't usually use it to train neural networks. Adaptive and decaying learning groups we saw can improve convergence because initially it lets you bounce out of the local minima and then come back into the global minimum. And then we saw techniques like rprop, which decouple the dimensions, actually help you converge better. And momentum methods, which emphasize directions of steady improvement, while de-emphasizing directions in which the solution is oscillating around, also improve convergence. And momentum is essentially you can think of it almost as a extension of R prop, where R prop ignores the magnitude and momentum does not. So we're going to look at incremental updates, and we're going to be looking at trend algorithms. Then in the next lecture, we'll be looking at some generalization techniques and aspects of the trade, batch norm, divergences, activations, stuff like that. So let's look at the issue of incremental updates. Now here's how we train a network. You're given a collection of input-output pairs at a number of locations, and we must estimate the entire function. This is how we set up the ERM. Oh my good God. Let me start this again, because so we're going to start off on talking about incremental updates. Here's how we set up the problem. We were given a collection of training samples which comprised input-output pairs, where you have for each input you specify the desired or the target output for the that input. And based on just this small number of samples, we would like to estimate the entire function. And so the way we did it was to set our network parameters such that it computed some initial function shown by the dotted red line over here. And then what did we do? What was the next thing we did at each step of the update? We would update the function based on the error. So what are these? This error is supposed to approximate. What does the error approximate? The area of the gap between the two functions. At which locations are we explicitly updating the error, decrementing the error? At the training samples. Nowhere else are we actually, we don't have data at other places, right? And so we adjust the function at all values for where we have training samples to make the outputs closer to the required value. So at the first two locations, the function that we compute is incremental. That way I catch you when you're sleeping, which you are. Okay, so at the first two inputs, the function is below the target function. So we would like to, what would we like to do with the function at those locations? Raise the function, right? And then at the next two inputs, the function is above the target function. What would you do? Lower the function at those points. And then the next one, the function is again below. So when you actually update your loss, your parameters based on minimizing the loss, you're minimizing the loss at every one of these points. So this is what you would expect would happen. Question? No, okay. That the function rises where it's below the target, and then it falls below where the training samples say it is above the target. You can only know the value of the function and or the gap between the actual and target values of the function where you have training samples. So you push it up here and there, lower it at those 2 points, you get a new estimate, and then you have new error, and then you're going to be doing the same thing again at the next iteration, where you'd be pushing it up wherever it's below and pushing it down at all the locations where it's above, right? So, and we keep repeating this process till it gets arbitrarily close.
Your mic, please. For a second. I'm sorry, they're saying it's low. You can keep going. See how mics are picked up. Sorry.
Folks on Zoom, I hope you can hear me. And so we keep repeating this process until we get arbitrarily close to the target function, right? Now, what is a potential computational disadvantage with doing things this way? Katrina.
So also could be a lot of data points and very hard to compute every time you update the entire data set.
So exactly, right? You're going to have to go through the entire data set, compute the error at every point before you update the function. But this is how we're supposed to be doing it, right? And so this is what we call a batch update. The problem of conventional gradient descent, we try to simultaneously adjust the function at all training points. And so this means you must process all of the training points before you make a single correction to the function. And that's what we call a batch update. this is what we call a batch update, right? Questions? Okay. Because if you don't, you have a problem. Okay. May I close the poll? Okay. The majority of you seem to think so. What can you tell me which of these? Somebody on Zoom. Can you tell me if the first statement is true? The actual loss function we minimize requires batch updates. Is that true or false? Zoom.
True.
Okay. Batch updates minimize the total loss over the entire training data. True or false? Also Zoom.
True.
Okay. And they optimize the actual loss function, Jihan?
No.
Okay. So they require processing the entire training data before we perform a single update. They're all true, right? So what would be an alternate update? So an alternate mechanism is to just say I'm going to be adjusting the function one location at a time. So some of you at least have tried working with putty, right? You try to take a lump of putty and you try to form it into shapes. Maybe you've definitely played with Play-Doh when you were in kindergarten. So what do you do? Now, if you were a robot with lots of arms, you take it and press it all over the place and shape it all at once. That's what batch update does. But then, as humans, maybe you're doing it with one finger. So you're going to be pushing it down one location at a time. But then what happens is that every time you press it down somewhere, something comes out somewhere else, right? Nonetheless, we do manage to shape our toys, even pushing it down one finger at a time. What is the secret to doing that? You push it in tiny bits very carefully, right? But if you do that, you can still get the job done. And so adjust the function at one training point at a time, but keep the adjustments small. So maybe pick up this point, and then you push up the function just at that one location. Strange things will happen at other locations, but maybe not too much. But this one's going up, right? Then you pick up another location, push that up. And if that's carefully enough done, the place where you corrected it the first time around doesn't get undone too much. And then you find that. Okay. Second map is making it worse.
Let me try one more thing. I don't know what it was. Seemed like it was fine before.
I'm sorry.
Thought that we might just use the ceiling mic.
There's a different channel.
No. Let's see.
My apologies, folks. These things happen. Technology isn't perfect.
Check. All right, that's the other channel. So frequency. All right.
Thanks, Paul. So folks on Zoom, can you hear me clearly now? Yes or no? Not sure. Okay. So anyway, going back. So we can just pick another location, push it down a bit, right? Where it's up, and keep doing this until eventually you've processed all the training points. So you pick one, correct it, and so you fixed it at all locations. And at each point, you keep the adjustments small. Eventually, you would have processed all the training points, so you would have adjusted the entire function. And in the process, you would have adjusted the entire function. Believe it or not, you can do it with greater overall adjustment than if you had processed all of the data in one single go, in a single update of batch. So here's what we would be doing. If you're doing incremental updates, in your batch updates, you went through the entire data, you computed the loss over the entire data, We used backpropagation to compute derivatives for every single training instance. You average these derivatives and then use the average derivative to update your parameters. Here, after every single training instance, we are going to be making our updates. So this happens within the training instance loop. Now, we can do this, and these, it's not, you don't have to just you don't just perform one pass over the data. You'd be passing over the entire data set each time. In the standard terminology of neural networks, we call one pass over the entire training data an epoch. But the optimization folks might have a different term. These are just terminology, right? So an epoch over a training set with t samples results in t updates of parameters, because after each training sample, you're making an update. So if you have t training samples, you will make t updates. And so here's what we have. One epoch is one pass over the entire data, and you're going to keep repeating. You're going to be passing over the training data multiple times. Each time you pass over the entire training data, we're going to call it an epoch. Now, you can't do it just any odd how. You have to be careful. So consider this. Let's say I have these 8 training points. And let's just say that my function is of a kind which is a curve, right? I'm trying to fit a function through these 8 training points. What is the ideal function that minimizes the error? The dotted red line shows me the target function. So the ideal function is just going to be as close to horizontal as possible, right? That's what I would want, because the function model itself restricts the function to being a curve, which is typically what you have with your neural networks. There's only so much the network can model. Now, if I loop through the samples in the same order, so if I go from left to right, process the first 4 samples, then I process the next 4 samples, which are, the first 4 samples are out to that corner, the next 4 samples are out to this edge. So here's what would happen. At the first 4 samples, all of them are telling me to decrease the function. And so it would go down, but then it's going to go up at the other side. It doesn't matter how carefully I do it. That's going to happen, right? Then I'm going to process the other side. What will happen? What's going to happen at the other side? Can somebody speak up aloud, guys? So that will go down, and this will come back up, right? And then I go back and repeat the process. What would happen? It's just going to keep seesawing, right? So you're going to get cyclic behavior, like so. It's just going to keep seesawing. So what would be a solution for this? How do you fix this? Yeah. You cannot just be going through them sequentially. You want to pick one from the left, one from the right, one from the left, one from the right. But in a large data set, you have no notion of what is left and what is right. You have to pick things at random. And so you want to go through the training instances randomly for this incremental update to work. Maybe pick one from here, adjust it a little, pick the next one there, adjust it a little. If you keep going through them randomly, you're not going to have seesawing, right? And this is critical for the whole process to work. Without this randomization, it will not work. You're going to end up with cyclic behavior. And so from my pseudocode, what does that mean? Just before I process each epoch, I'm going to be shuffling my data, permuting the order of my data, which ensures that I'm basically going through them randomly. Within each epoch, I'm randomly permuting all of my data. Questions? Okay. On Zoom? Nothing complex. So the story so far, in any gradient descent optimization problem, presenting training data instances incrementally can be more effective than presenting them all at once, provided the training instances are presented in random order. This is called stochastic gradient descent. Yes?
In the previous slide, in the pseudocode, would we have a fixed learning rate over the different?
We'll get to that, right? I'm going through these things one step at a time. Good question. And so we call this stochastic gradient descent. Why would we call it stochastic gradient descent? you're randomizing the order in which you pass through the data. Therefore, it's stochastic. It needs to be stochastic for it to work, right? Now, why would this process of incremental update work, and under what conditions? So, for understanding the why, let's look at a very simplified example first, right? Let's look at an extreme example. Now, my loss function, my batch loss function, is an average of losses over many training samples, correct? So the batch derivative, meaning the average derivative over all of the training instances, is the average of the gradient over all training instances. Now, if I have a whole collection of training instances, each one of them has a different loss, because some of them are going to be, at some training instances, the current function may be higher than the target, at other places it may be lower. Any odd thing can happen. So if you look at the derivative of the loss for a single training instance with respect to the parameters, it's going to give you some direction. And these are not all going to be lined up, right? They're all going to be in arbitrary directions. Each one of those blue arrows in my figure to the right, the black dot shows you the current estimate. And so the figure to the left supposedly shows the loss, and the figure to the right shows the parameter space. So that's the floor. And at the current location, you have many training instances, and the derivatives, the gradients of the loss for the individual training instances all point in different directions. The batch gradient is the average of all of these arrows, right? It's the average of all of these divergences. And so that red arrow, which is the net derivative, which is the average of the derivative of all the training instances, is the direction in which you want the parameters to shift. But then consider this extreme case where all of my training samples are the same. I have 100,000 of them. So is the average derivative going to be different than the derivative of for any single instance? Yes or no? No, because they're all the same, right? So what happens when I first go perform a batch update? I process the entire lot and make an update. I could have saved myself that effort. So here, the average is simply going to be the same as every one of these guys. And therefore, if I just do a batch update, after a single pass through the data, you're going to make a single correction, like the figure shown to the left. Whereas if you made an update after every single training instance, even if the step sizes, the learning rate is much smaller, eventually you're going to get a much larger number of updates, and so the net correction is going to get much larger. So stochastic gradient descent over here is going to get t updates of the parameters, whereas batch descent is going to get just one update, right? So is this the only condition under which it would work? This concept would work. What do you think? Can you tell me what you could do which would still be, where this idea would still hold? How you could, what could happen to the data? If they're all just a little perturbed, like so, this concept should still hold, right? Correcting after each one still should give you more or less the same effect as, should give you t times the effect as correcting with the average, because they're very close. So when do you think this is actually going to, so what would happen as the data got more and more sparse and more separated? The gap between incremental updates and batch updates is going to go down, right? And so as the data get increasingly diverse, the benefits of incremental updates decrease, although they won't entirely vanish. Making sense to everybody, right? Now this is just a hand-wavy kind of high-level explanation, but we can actually get a little more formal, right? So, but first, let's look at the considerations. The problem with incremental updates, if I have, is this. So let's say I have this problem. I have this bunch of training data points, and I want to find a linear regression, not an affine regression, a linear regression that goes through origin. So clearly, this red line is the correct solution for this collection of dots. How do you get this red line? Every single, when you're trying to find a regression, you're projecting every point onto the line. In the process of projection, you're going to get an error, which is the perpendicular distance between the point and the line. And you would find the line which minimizes the total squared perpendicular distance between the point and the line. This is your linear regression. Now, this is what you would get if you were performing batch updates. You were looking at all of the training data and then learning your parameters all at once. But then, if you were performing incremental updates, you start at some point. The first data point that you see is this guy. I can swing the line right down to that point and make the error 0. Then, because remember, you're correcting the error for each point, right? Then the next point I see is this one. The line is going to swing up and go out there, right? Then the next point I see is this. The line is swinging here. The next point I see is this. The line is swinging there. It's going to keep oscillating around. Will it ever stop? Will it ever come to a single unique solution? It will not, right? So how would you fix this? Yes, Chetan?
Keep like a running average over all the points, so slowly.
This is incremental, right? So
Smaller step size.
smaller step size, how?
The learning rate that you use should probably be lower than what you use for any.
Even then it's going to keep oscillating. It's not enough for the learning rate to be small. There's one step more. And what would that be? You want the learning rate. Eventually, when you process infinite points, you should be confident that you've got the answer. The next point should not change the solution, right? Which would mean that after you processed a very large number of points, the n plus 1th point where n is very large must have infinitesimally small or 0 effect on the parameter updates, which means the learning rate must have gone to almost 0, correct? And so you want the learning rates to shrink with iterations. The first time around, maybe you get all the way up there. The next time around, you don't correct all the way to the point. You stop somewhere short, right? And then the next time around, you don't stop, go all the way to the point. You stop somewhere short. And you keep doing this. And with increasing iterations, it will swing less and less. How do I get rid of this thing on the screen? It's not on my screen. Okay. And so with increasing iterations, it will. Can we get rid of this thing on Zoom? Okay. Thank you. So it's going to swing less and less towards the new point, right? And so in incremental learning, we're going to update the model to always minimize the error on the latest training instance. But for this to work, we want to shrink the learning rate with iterations. And so when you do so with increasing iterations, it will swing less and less towards the new point, and eventually it will arrive at the correct solution and not move too much when it sees additional points. But for this, are there any conditions on the manner in which the learning rate goes down? So obviously, you can't just do it any odd how, right? So it turns out there are some conditions. There are the first condition, of course, is that the learning rate must go down, right? But the second condition is this. You have to be able to deal with the worst case scenario, right? Now, let's say I have my optimum is out here. That's my optimum. And this is my initial estimate. So now let's say the upper bound, your function never has infinite derivative, right? So the upper bound on the derivative is some fixed value. So let's say this is my upper bound. This is how large the derivative is going to get at any point. Okay? What is the minimum number of steps that I would need to get there, get from the initial point to the optimum? It's going to be the distance divided by the upper bound on the derivative, right? Now, if I keep, so let me call the upper bound on the derivative u, right? So, and let's say the learning rate in the ith iteration is eta r. then what is the total distance covered, or what is the upper bound on the total distance covered from the initial point in infinite iterations? That is going to be u times eta 0 plus u times eta 1. So this is going to be u times eta 0, right? This is your derivative, the upper bound on the derivative. The next time around, you're going to do u times eta 1, right? The next time around, you're going to do u times eta 2, and so on. So the distance covered is going to be the summation of, this is the upper bound because u is the largest derivative. In reality, it will be even less. So u times the summation of all the u etas, which is u times summation I eta I. Correct? This distance, which is the largest distance you can cover, must be enough for you to get from your initial point to the optimum, right? What is the upper bound on how far away you can be from the optimum? You can be infinitely far away, correct? So what can you tell me about this guy? What can you tell me about this? Considering that you can be infinitely far away, what does it tell me about this term? Surya. Someone.
Summation is infinite.
Pardon me?
No, eta should be infinite.
Yes, this has to be infinite, right? If you're infinitely far away, eventually you must get there after infinite steps, right? And because u is a finite number, this means summation I eta I should be infinity. For the incremental updates business to work, you should be able to cover infinite distance eventually. That makes sense to everybody? Right? At the same time, you want the step size to converge, right? So how would you make that a convergent series? The other way that comes out is that you want summation I eta I squared. Your learning rate is always less than 1, right? Or eventually becomes less than 1. Has to be finite where c is less than infinity. So the sum of the squared learning rates must be finite, but the sum of the learning rates must be infinite. But making the sum of the learning rates infinite guarantees that it doesn't matter how far away you are, you're eventually going to get to the solution. But making the sum of the learning rates finite ensures that it converges, right? The step sizes keep getting smaller, and so you're not going to be bouncing around permanently. Now, what kind of learning rate satisfies both properties? Can someone suggest something? I want a series of etas such that the sum of the series goes to infinity, but the sum of the squared series is finite. Yes, Joshua?
Eta was 1 over x.
Thank you. Right? So eta I, okay, is 1 over I. Or if you're starting from 0, then I can say I plus 1, same thing, right? This is a what kind of a series is this? It's a harmonic series, it's divergent, right? What is the summation of 1 over n? It goes to infinity, but each step is smaller than the previous step, right? And so it's going to converge. The 1 over n squared is convergent, but 1 over n is divergent. So this is the kind of learning rate schedule that you will want. And so in incremental learning, you update the model to always minimize the error on the latest instance, but you must shrink the learning rate with iterations for convergence so that the correction for individual instances with the eventual minuscule learning rates will not modify the function. And yeah, so this is the updated pseudocode, which says that the learning rate now is actually changing with function with iterations. It keeps reducing. You still need to permute your input, of course. And the condition on the learning rate is this. The sum of the learning rates must be infinity, but that means the entire parameter space can be searched in infinite steps. Whereas if it's not, then if you start at the wrong point, then it doesn't matter how much time you spend, you're not going to get there, right? At the same time, the sum of the eta squares must be finite. And so the fastest converging rate that satisfies both criteria is going to be 1 over k, as someone pointed out. Is that you? Yeah, that was Gyanyang, right? Yes.
Does this sort of imply that there's an upper bound on how many training instances are actually used? After a certain number of points of updates, you're not changing the gradient. Does it mean that after a point adding training?
So you're speaking of eventually, yes, right? Because the learning rate, if you're adding novel training points. Yeah. So, and more generally, we use heuristically derived learning rates. You might have encountered these in your homework, but then they all satisfy this property, right? If you look at the sum of 1 over eta squared, the sum of eta squared, it's always finite. And sum of etas, well, it may not be infinite, but it's going to be very large. If the loss is convex, SGD, stochastic gradient descent, will almost certainly get to the optimum. And if it's non-convex, it's going to converge to a local minimum. Right? So how well, okay, everybody with me so far? Any questions? Yes, Chetan.
How does this handle what we talked about last time with you're going to start with larger running rates to get outside of local?
Yeah, so this still works the same way. Your initial eta can be very large, right? So long as it's shrinking and satisfies the two properties, you're good. And in fact, this sort of lines up with it perfectly. Again, nice question. So how well does this work? This is an example I pulled off the web for someone who ran k-means clustering on a bunch of data. And so, k-means is it's also an iterative algorithm. The solution you get is going to depend on the initial estimates you start with. So if you run this multiple times, each time you're going to get a different solution. So the red curve shows how the error decreases with iterations when you're performing stochastic gradient descent. The green curve shows you how the error decreases when you're performing batch updates. The bar shows you the variance in the error across different runs, because each run is going to give you a different, depending on how you initialize, you're going to get different values, right? And so what do we find? The stochastic gradient descent converges much faster, right? But it also varies a lot between runs. Also, it's much poorer than batch descent. Does everybody see that over here? Right. So let's go back and dissect this a bit and see why this is the case. Now, but before that, here's a point. You need more time? Okay, let's try this. Is the first statement true? Is SGD an online version of batch updates? Yes, right? Online literally means incremental as data comes in. SGD can have oscillatory behavior if we do not randomize the order of inputs, true or false, right? It can converge faster than batch updates, but arrive at poorer minima, optima, true or false? True, okay. SGD convergence to the global optimum can only be guaranteed if step sizes shrink across iterations with sum to infinity in the limit. True or false? Also true, right? The 4 points that we've just seen. So, questions? Yes. Yes, sir.
Can we guarantee that SGD will converge to global optimum?
To the global, you can never converge, anything will converge to the global optimum when you're doing gradient descent or associated techniques, unless you follow some gradient descent type techniques cannot be guaranteed to.
Okay, so, but why is the fourth one just correct?
So you have a point over there, right? It can only be if it exists and if it goes there. In that case, you still expect it to. This condition for this, if you have a perfect bowl and you're infinitely far away, you'll need infinite steps. Yeah.
Convex, right?
It's convex. I'm sorry. I should correct that. You had a question?
I have the same question.
Okay, you guys caught me. Thank you.
So the condition is that a loss function must be convex and then
Otherwise, it's going to be a local optimum. Good point. Good catch, both of you. So now let's go back and look at why this variation happens, right? Why does this variation happen? And this has to do with statistical properties. Remember, now for this, let's start by looking at. So you had the actual function, and then you had the function that the network computed, and this region was the actual error, right? But then the way we, in principle, what we were trying to minimize sort of computed this, this area in a specific manner. At each point, you had an error, right? So if you checked all of these points and aggregate found the average error over all of these points, all infinite points, that gave you the error that you actually wanted to minimize, right? But then if these training samples themselves have some probability distribution, you also have to consider the importance, relative importance of each training point. And so our error was the integral of the divergence multiplied by the probability of the point integrated over the entire input space. So we were trying to minimize the expected divergence because you're treating the input itself as a probabilistic variable, right? And you are trying to minimize the error at every point, which is basically minimizing the average error, right? But by the same criterion, at each point, if I treated this as these x as a random value, corresponding to each x is an error, right? So this infinite set of x's has an infinite set of errors, and that infinite set also has a variance, right? Everyone with me? Because x is a random variable, the error is a function of x. And so I get two terms. One is the expected value of the divergence for each x, and then I have the variance of the divergence of x. These two are the properties of this error, right? What are we trying to minimize of these two? What are we trying to minimize? The expectation. If you minimize the expectation, if you send it to 0, the error goes to 0. There will be no more variance, right? So this is what we're trying to minimize. And now let's take a look at what happens when we actually take the empirical error. The empirical error is computing the empirical loss, empirical risk is computing the error at a bunch of points and taking the average, right? So you're saying loss equals 1 over n summation I divergence of xi. So if I take the expectation, what does this expectation mean? What this means is that, let's say, you have a very large number of people in class, and each of us collected our own training data, right? And so if each of us collected our own training data, each of us is going to get a loss. And so if each of us got a loss, our loss, none of our individual losses is going to be the expected error, correct? Because we're just collecting random samples. But if we average the losses of all of us, what would we expect to see? Juho. So let's say you have your own training data. He has his own training data. Everybody has their own training data. So you're going to compute a loss, right, from the current parameter sets. So we just take all of our losses and average them. What would you expect to see? What is that value going to be? So that is like saying I'm going to be taking the expectation of the loss, right? So this is the expectation of the loss. It's going to be the expectation of this guy, which is 1 over n times the expectation of divergence of x, which is 1 over n times the expectation of the divergence of x, which is the expectation of the divergence of x. So what this literally means is that if you ran the same experiment bajillions of times, where you collected, and each time you collected a fresh set of training data, across all the runs, the error that you compute, the average error that you compute, is actually going to be the loss that you are trying to minimize. So this loss is what we call an unbiased estimate. The empirical risk is an unbiased estimate of the true loss. Over infinite experiments, the average is going to give you the true loss, right? So, which is why we minimize this guy. We say, on average, this is going to be the true loss. So if I minimize this, maybe I will actually be minimizing the true loss, which is the expected divergence, right? But then what happens? Will each of us get the same loss? So if you look at the collection of losses, the average is going to be the expected divergence. But what about the variance? We have a collection of losses, and each of us is going to see a different loss, right? And so there will be a variance across the set. What is that? So the variance is going to be, if I write this down, variance of 1 over n times summation I divergence of xi, right? And each of my training samples is independently chosen. So what do we know about the variance of the sum of independent random variables? Someone has to answer that. Pardon me? The sum of the expectations. I'm speaking of the variance. What is the variance of the sum of independent random variables? Sum of the variances, right? They are independent. And so you have, this is going to be 1 over n squared, because variance is a squared term. Expectation of the sum of I divergence of xi, which is going to be 1 over n squared times summation over I variance of the divergence of xi, which is going to be 1 over n squared times n times the variance of divergence of xi, of x basically, which is the variance of the divergence of x divided by n. So this is what, if you're averaging n training points to compute your loss, then across runs, the variance that you will get in the loss is actually going to be the variance of the random variable itself, the variance of the divergence as we originally stated it, divided by n. Okay. Now this may not make a lot of sense right now, but bear with me. We'll see some pictures, right? And so the variance of the empirical risk is 1 over n times the variance of the divergence. So which means the variance of the estimator is proportional to 1 over n. As you increase the training set size, the difference between the losses that you will get across different training sets is going to decrease as you increase the training set size. And it's going to decrease in inverse proportion to your training set size. And so if this variance is large, what it means is that across runs, we will end up at completely different points, because no two training sets are going to give you the same optimum, right? And so that's the thing. So when we have a very large training set, you're going to get, the variance is going to be smaller, and so you're going to get closer to the same solution each time you run the optimization. If you're using stochastic gradient descent, at each point you're looking at a single sample, right? Just one sample. So your single sample error is simply the divergence at that sample, right? What is the expected value of the divergence? The expected value of the divergence is simply the expected value of the divergence. So this is, if you look at this, the expected value of divergence of x is just the expected value of the divergence that we had, which is the same as this guy here. So this is still an unbiased estimator, meaning what it's saying is that if all of us took only one training point, computed our loss, and then averaged all of our losses, that's going to be pretty much the same as the true loss that we are trying to minimize. So this is also an unbiased estimate of the expected error. But the variance is going to be the variance of the divergence itself, right? Because you just have one point. It means that if you look at all of our losses, the variance is going to be much larger than if each of us had a collection of training points. So the variance of the sample divergence, if you just in the batch case, we found that in the batch case, we found variance of loss is 1 over n times the variance of the divergence. And in the SGD case, because n is going to be 1, each time you pick a sample, your training set size is only 1, right? So for SGD, this is batch. And for SGD, variance of loss is simply variance of divergence. So what is this telling us? That across runs, SGD is going to have a much greater variability than if you just had batches, than the batch processing, which is why you saw this strange picture. But then let's see some pictures, because that, math is math. And I don't know about you, math doesn't make sense to me, right? But let's look at some pictures. Here's the thing. I'm trying to approximate the blue curve, g of x, with my red curve, which is the current network, right? And now, I don't have the entire function, so I'm going to be picking some random collection of training points. If I chose these training points, then I'm going to be approximating the shaded area by the sum of the lengths of the error bars, right? The colored segments, colored line segments. And that's going to tell me that the function has to be shrunk to the left. The function has to be raised to the left. It has to be shrunk here. It has to be shrunk here, and it has to be raised to the right? So these training instances are giving me this information. But suppose you went and chose a different set of training instances, and your training instances were these guys. What information would you get from these training instances? So the function must go up everywhere, right? And then Chapin went and chose his own training instances. What would it tell him? It must be pushed down everywhere, right? Each of us, based on the specific training samples we got, each of us is going to get a different Q from the training samples, right? So how can you fix this? How would you fix this? Naman, how would you fix it?
Maybe take smaller learning steps so that
So again, no, I can just take a lot more training samples, can I not? If I take a lot more training samples, I'm much less likely to make that error. So this is what this entire business about variance tells you, that each time you take a training set, you get a different lesson from the training set. The only way to decrease the variation across training sets is to just have a much larger training set. Making sense to everybody? Right? What happens with SGD? I have only one sample. This sample tells me I'm fine. There's nothing needs to be done to the function. This sample tells me, oh, the function's got to be pushed up. this guy tells me the function's got to be pushed down, right? And because you have only one sample at a time, the variation between the Qs that you're going to get from sample to sample is going to be enormous. It's very large, which is why the loss itself, the loss function changes dramatically, right? With training sample to training sample. So you have a much greater variance in the loss function, and therefore you get this behavior that across runs, the solution can swing around wildly and can also be much worse. Whereas with the batch, that doesn't happen, right? So what would be a solution? How do I fix this? I know that processing things incrementally makes things better, faster. But I have this issue.
Don't go one at a time, maybe like really small.
Thank you, right? So is there a good medium? SGD uses the gradient from only one sample and is high variance, but provides significantly quicker updates than batch. So is there a good median? Choose a random subset at each time. So maybe at the first type, pick this subset, right? Then at the next iteration, you're going to make some corrections based on this. Then at the next iteration, you pick a different subset. You're going to make some corrections based on this. And again, just like you would in SGD, you keep the adjustments small. So this means that you actually get a lowered variance because you're looking at a number of samples. At the same time, you're getting some of the benefits of SGD that a single pass through the data gives you many more updates, right? And so here's what you would be doing. You would actually be processing the data in batches of B, size B. These are what you call your mini batches. And you'll be computing your derivative, average derivative over the mini batch, which is what you would be using to perform your correction. So mini batch size, shrinking step size, and you still have to shuffle your training data between epochs. Okay. So how does this work? Now, why does this work from the math perspective? Again, our point was that if the variance of the loss was variance of the divergence, right? This is the variance of the gap between the true and expected functions. Then when you use for a batch size n, variance of the loss is variance of divergence by n. Right? This is for a batch size of n. So when I actually perform stochastic gradient descent, so this is my batch size, and this is what, suppose my entire training data is n, right? This is the lowest my variance is going to get. And for a batch size of 1, let me start this. This is the variance of x, variance of dive, right? So this is the variance that I would get between runs if I were using a pure stochastic gradient descent. This is what I would have with a full batch. And the variance falls as 1 over n, right? So how does that fall? That's going to fall very fast, right? And that's why increasing the mini batch size rapidly makes things more stable. Again, how far? There's a point beyond which the reduction in variance is probably not worth your time. And so there's some sweet spot out here where your variance is low enough that you can expect some stability across runs. At the same time, you're able to process the data, get many more updates per epoch. And so firstly, the mini batch loss is also an unbiased estimate of the expected loss. And what happens? And the variance of the mini batch loss is proportional to 1 over b, where b is the size of the mini batch. And what we find is that this actually can begin to approach the actual variance of the true empirical risk. And so gives you the gains of SGD, and computational gains of SGD, without giving you too much of a loss in terms of variance. And so if you actually look at the behavior of mini batch versus SGD versus batch descent, the red curve is a stochastic gradient descent, one instance at a time. It converges very fast, but the variance is very large between runs, and the optimum is much poorer. Batch descent, the variance is much smaller, and it converges, but converges very slowly. Mini batch descent, the x-axis is training time. You can see mini batch descent converges almost as fast as stochastic gradient descent. It converges, however, to almost the same optimum as full batch, and the variance across runs, as shown by the bars, is also just almost as small as full batch. So this is what we will actually do when we actually train our networks. We're going to be using mini batch. So then, so again, just one thing. These pictures over here, for these runs, they actually computed the loss over the entire training set. But when you're performing mini batch descent or stochastic gradient descent, you're always only seeing the loss on the latest batch, right? So that number you get is not indicative of the empirical risk over the entire training data. So it's always a guess. The plots that you see in your training, they are not the truth. They're only tracking the loss on the latest mini batch, whereas what you want to track is the loss on the entire data, but you're not going to be computing it, right? That would be kind of pointless. So that's a cut. And so we come up with various heuristics like using running averages and such like to plot it. But anyway, so in practice, training is usually performed using mini batches. You want the mini batch size to be as large as you can fit into your memory, simply because the larger the mini batch size, the lower the variance across runs, the more stable the run is going to be. And so mini batch size is typically said to be the largest that your hardware will support without compromising compute time. And larger mini batches means lower variance, but larger mini batches also means fewer updates per epoch. So there's the trade-off. If you want more updates, you want to reduce your mini batch size. And so the sweet spot often depends a little bit on the problem and the data that you've got. Convergence depends on the learning rate. And our standard technique is to fix the learning rate for a while till things converge, and lower the learning rate till it converges, and so on. But look, regardless of the learning rate schedule that you use, you will find that the learning rate schedule has this property that the sum of the learning rates is large, but the sum of the squares of the learning rates is small, because it needs to have that property, otherwise things will not really converge, right? And then you have advanced methods. We have adaptive updates where the learning rate itself is determined as part of the estimation. We will look at that, but first there's a poll. Watch for a few seconds. You want a few more seconds? No, Quentin's my clock. He's setting his laptop. Okay, so, all right, guys. Can you answer this question? This all 4 on Zoom. Mini batch descent is an online version of batch updates. True or false?
True.
True.
It's faster than SGD when the batch size is 1. True or false?
False.
They're the same thing, right? Mini batch updates with the batch size of 1 as SGD. The variance of mini batch updates decreases with batch size. True or false?
True.
And mini batch gradient approaches batch updates in variance, but SGD in efficiency when we use vector processing in large batches. True or false?
True.
Right? So the second one is false. So here's the story so far. presenting training instances one at a time can be more effective than full batch training, provided they are presented in random order. For SGD to converge, the learning rate must shrink sufficiently rapidly with iterations, otherwise the learning will continuously change the latest sample. SGD estimates have higher variance than batch estimates, and mini batch updates operate on batches of instances at a time. So these estimates have lower variance than SGD. Convergence rate is also theoretically worse than SGD if you actually work out the math, but then you are able to perform batch processing, so things actually work out. So the pictures I drew don't tell the mathematical story. The mathematical story is a little different, but in practice, what we observe follows the pictures that I just drew. Okay. So now, let's go back, and the last thing that we spoke about in the last class was trend algorithms, momentum, and such like, right? Turns out that these things are actually going to be, while they are very useful when you're performing batch updates, they are a lot more useful and necessary when you're performing online techniques like mini batch updates and stochastic gradient descent. And there's a reason for that. Before that, let's just quickly revise how we performed momentum-based updates. In the momentum-based updates, we performed a running average of our gradients. So suppose you had the gradient, so let me call delta this nabla L0 as my gradient at my first iteration, right? So this one gave me some delta W equals minus of some eta times nabla L0, right? Then at that current estimate, the next step, I got a new gradient. So the new gradient is going to be L1. So from this, instead of using this directly, I'm going to use this guy, some average of this guy and this fellow. So I'm going to say delta W is going to be some beta times delta W, so the previous value, minus nabla eta times L1. So I'm not using this directly. I'm averaging it with the previous step. And then at the next step, I'm going to get maybe some other error, gradient of the current estimate. But instead of using this directly, I'm actually using a running average with this one, right? And so we have the same minus eta times L2, and so on. So we maintained a running average. And the point of maintaining a running average is that if your gradients are swinging around in some directions, because you keep adding them, upward and downward motions will cancel out. Whereas if the gradient is consistent in one direction, they're going to keep, they're going to stay consistent. So it gets longer in directions where the gradient retains the same step sign, and shorter in directions where the sign keeps flipping. But here's the thing I want you to keep track of. This correction is actually a running average of all of the gradients computed. Instead of using the latest gradient, you're using the running average of all of the gradients, right? And so that's how it worked. You took a step. Suppose this was your current step. Then you computed the gradient at your current step, and you took a step against the gradient, but then you added some factor times your previous gradient in, and that gave you the new step, right? So this was your momentum-based method. Remember, we saw this. And then we also saw that we could do things slightly better. What was that? We could change the order. So we said, instead of doing this, so this was the momentum update, right? Step one, you move against the gradient, then you add in some fraction of the previous step to get the new step. Change the order. I can first take a step along, a reduced step along the previous direction, and then compute a gradient update, which takes a step against the gradient, and that gives me my new correction. But then, so the next step is going to be, extend the black, and then take another gradient step. And this was Nesterov's method, right? And we also saw that if you compared the gradient-based method versus Nesterov's method, this actually ends up being better. So the first point, momentum versus Nesterov's. The blue curve is showing you the momentum method. You take a step against the gradient, and then add some scaled version of the original black line. So you don't quite directly go towards the center, whereas Nesterov's method, extends the black line by the red line and takes a step against the gradient, and it gets to the center much faster. So this is, so it's Nesterov's method is probably more optimal than standard momentum. But that's not the point. These are just the two techniques. It turns out that when you are performing stochastic gradient descent or mini batch descent, you have a lot more variance, right? So the loss function doesn't change from the loss function changes from step to step in our batch update only because of the location at which you're computing the loss, right? But the function itself doesn't change. It's always the same loss function. In mini batch updates, your loss function itself changes because at each point you're looking at each update, you're looking at a different set of training instances. So when you compute the gradient of your loss function, it's going to be wiggling around a whole lot more because you're not following the average, you're following some subset. And so as a result, you're going to find that your gradients are all over the place. And this fluctuation is going to be smaller as you increase your mini batch size, but nonetheless, the fluctuation is going to be there. And so now, in order to deal with the fact that you're looking at a different set of training samples from iteration to iteration, it becomes much more necessary. I think Chetan pointed this out some time ago, right? That you want to take a running average of the gradients just to make sure that you're not, wildly chasing the latest sample. And so this is where these momentum methods become a whole lot more important. You're still going to be using the momentum update rules, except that the momentum-based running average that you're going to be performing will be using the latest gradient to update the running average. So in the momentum-based method, this update over here, that's going to be the gradient computed on the latest mini batch. Or if you're using Nesterov's method, then this gradient that you're going to be computing over here, this update is going to be the gradient on the latest mini batch. Right? Questions? So now, so we've looked at two things. We've looked at a series of things. So one last topic, right? When you are looking at gradient descent rules, here was the gradient descent based update. At each point, at each current estimate, you are taking a step against the gradient, but the step depended on two terms. What are the two terms it depended on? Guys? Learning rate and gradient, right? So there are two different terms that come into the picture. Which of these does the momentum-based method actually fix? The learning rate? The gradient, you're taking a running average of the gradient to take care of the fluctuations, right? So the momentum methods fix this term to reduce unstable oscillation. Your gradients are up and down and up and down and up and down. And so you take a running average and smooth out the gradient, and that's what the momentum-based method is using, right? What about this guy? This too can be dealt with in a similar manner, right? So, and for that, let's go back and look at pictures, right? Now, here are three different sets of gradients. The running average is going to be the same in all three cases. Along the horizontal direction, they are all going the same way. In the vertical direction, the oscillations are canceling out, right? But then the learning rate, what can you say about the learning rate in the horizontal direction? Can it be high? Should be higher? So okay, just look at this picture. In the horizontal direction, do you want the learning rate to be high or low? High, because you're going in the correct direction. In the vertical direction, do you want the learning rate to be high or low? Because it's swinging a lot. You don't want to be following it, chasing it all the time, right? And so I want to have separate learning rates for each direction. And I'm going to make the learning rate consider how much the estimates are swinging in that particular direction. And so here's what I will do. So you can look at that. So I have some numerical examples. Just a toy example here. If you look at the x coordinate, the gradients are always positive. In the y coordinate, the gradients are up and down. Obviously, the learning rate should be lowered for the y coordinate because you don't trust those gradients. Whereas for the x coordinate, you trust the gradient. So you want to keep it higher, right? And so we are going to have a learning rate which is inversely proportional to the root mean squared value of the motion. So if you look at this one here, you will see that the total motion along the y direction is much larger. You're just moving a whole lot for nothing. Or over here, if you just measure the total length of the lines, the total length is tremendous along the y direction, but the net movement is zilch. Whereas along the x direction, the total movement may not be less, but every step counted, right? So we are going to make the learning rate inversely proportional to the total movement. Now, you can't just take the average. The average, the positive and negative movements are going to cancel out. You want the total movement, so you'd want to take the absolute values, which are a bit of a pain to compute. So we will take the root mean squared value, right? And so what that means is that if I have something like this, I'm going to say 2.5 squared plus 3 squared plus 2.5 squared plus 2 squared plus 1.5 squared. That's my sum squared value. I divide that by 5. That's going to be my mean squared value. I take a square root of that. That's my root mean squared value. If that is large, I'm moving a lot. If that's small, I'm not moving very much, right? And so depending on how much I'm moving, I'm going to lower my learning rate. And so here's just some notation. I'm going to write partial squared. It really means it's the square of the partial. It's not the second derivative. And so I'm going to write expected value of partial square. That's not the expected value of the squared derivative, second derivative. It's the expected value of the square of the derivative, just for notation, okay? And so here's what we will do. I'm going to, in your momentum method, we maintained the running average of the, what did we maintain running average of? Gradient, right? Here I'm going to maintain a running average of the square of the gradient, right? Gamma times the current estimate plus 1 minus gamma times the latest derivative squared. Not the gradient, but the derivative, right? And so that's my sum, that's my mean squared value. If gamma lies between 0 and 1, this is going to be my mean squared value for the derivative. And I will have an initial learning rate, whatever it may be, but I'm going to divide it by the square root of the mean squared value. So this means that I don't have to adjust eta by myself. It's going to get adjusted simply by lowering it or raising it based on how much it's swinging in that particular direction. You would expect that if you overshot an optimum, then you'd begin swinging, and it's going to shrink. Whereas if you're going in the same direction, you're not going to be swinging, so it's going to increase, right? So you expect the kind of behavior that we want, where it shrinks the learning rates so that you get to an optimum, to happen naturally, right? So this was what was called RMS prop. This is the learning rate. This is still using the gradients, but the learning rate is inversely proportional to the mean squared value, so root mean squared value. Now note the similarity to R prop. In R prop, we only use the sign of the derivative, right? Now here, if your derivative were constant, if the slope were constant, what happens? The root mean squared value and the value are going to be the same, because all the derivatives are the same, so their squares are all the same. The average of the squares is going to be simply the square of the derivative. The square root is going to be the derivative. It cancels out. All you will be left with is the sign. So this actually looks a whole lot like R prop, right? So far so good, right? We've come up with a RMS prop, only the momentum method only fix the gradient. RMS prop only fix the learning rate, right? what is the obvious next step? Combine the two. Combine the two, right? That's we want to learn both. And so this was the technique that we call ADAM, where you both maintain a running average of the gradient out here and the squared term. Okay, I'm calling it V, but it's really the squared term, right? And so, and the update rule is simply the same as before, except now you not only have you're not only scaling the learning rate by the RMS value, you're also using the running average of the gradients to get the best of both worlds. There's one little quirk over here that typically what happens is that initially you're going to be setting the, because you're using running averages, your delta is typically going to be close to 1. So if delta is close to 1 and your initial estimate for all of these terms is 0, then in the beginning, 1 minus delta is going to be a very small value. And so for the running averages to catch up with something meaningful, will take many iterations. And to prevent that, there's a division over 1 over 1 minus delta raised to k or 1 minus gamma raised to k. That's just an engineering fix, right? To make sure that things actually progress fast. But again, we are using running averages, and the parameter which we use for the two running averages, they can be different. Delta and gamma can be different. But you get the idea of how ADAM works, right? And so there are many other variants of the same thing. You know, add a grad, add a delta, add a max, but they're basically the same variants of the same thing. And the one that you would use most is ADAM, right? There's one final poll, and then if you'll bear with me for a couple of minutes, I'll just show you some pictures, or you may go without this. Okay, all right. Can I go around here? So you at the very back, can you answer the first one? True or false? False. And Josh, what about the second one? True. And Akriti, third one. And Sushant, fourth. And Cheng, fifth. Chonghan, yeah. The last one. Okay, somebody else take the last one. True. Okay. Wait a minute. Where were my answers? Yeah, only the first one is false. Yeah, vanilla SGD does not consider the long-term trends of the gradients. Pretty much everything else is true, right? Thank you, guys. There are some videos that I picked up from Alec Radford's website. He shows you how different techniques converge on different functions. And you can see some very cool behavior. And what you find is that when you get to functions where the slope is constant, RMS prop doesn't do a very good job, because eventually the step size becomes fixed with slope. SGD, he shows, here's a nice one. The red one is SGD, just sat itself in the saddle point and it's perfectly happy sitting there. Pretty much every other technique heads down. And interestingly, you can see that Nestrov's method, even without the correction, without the adaptive learning rate, tends to do very well on most problems. In fact, you can see Nest catches up the pink line. So it depends. You can actually analyze the shape of the function and figure out how each of these techniques will behave, because you know exactly what they're trying to do. Anyway, I'll stop here. Thank you for your time. I appreciate you waiting a couple of minutes.